In this video, we're going to start looking at the graphs of sine and cosine. First, let's define a periodic function, which is what we're going to classify all of our trig function graphs. These periodic functions have cyclical graphs where the pattern repeats itself. So let's build out our sine graph. We're going to graph our parent function y equals sine x. And we're going to do this just by making a table of values. And we're going to use 5 values for x: 0, pi over 2, pi, 3 pi over 2, and 2 pi. Sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. 3 pi over 2. Sine is -1. And 2 pi is 0. This is what we're going to call our landmark points. Now, different people have different names for these special points, but essentially we're going to use these same 5 points to graph all trig functions, just implementing whatever transformations we need to do. So they won't be the same ordered pairs, but we're going to use these points to build off of those transformations. So I've got a grid here. We're going to start plotting these. For these 5 points, what they do is they actually create 4 equal segments or 4 equal sections of the period of sine. The period of sine is 2 pi. So I'm just going to mark 2 pi off somewhere on this grid. I'm trying to space it out as much as possible. And then I'm going to start dividing by 4s, or I'm sorry, dividing by half. So taking the full 2 pi, dividing it by half, then each of those halves dividing it by half to give me some pretty good equal sections. Here's our pi over 2, pi, 3 pi over 2, and 2 pi. The min of this function is -1. The max is +1. Sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is -1. And sine of 2 pi is 0. So this creates this really pretty curved wavelength looking graph. And really what the arrows indicate that this is going to continue on forever. So just a quick sketch of our sine function. Over a larger period. What we're really looking at though is just this section here, which is representing one period, which we've graphed here. But that pattern would continue on and on in both directions. The graph for cosine, y equals cosine x, again, starting with those same 5 values of x and evaluating cosine of those values. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. Cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is +1. So you can even see in these table of values where we start seeing the values repeat themselves. So we went through that 1, 0, -1, 0, and now we're back at 1, where we would then continue on 0, -1, 0, 1, so on and so forth. I'm going to set up my horizontal axis the same way, marking off the length of my period is 2 pi, and then dividing that into 4 equal sections, starting with half, and then breaking those halves into half. Here's our pi over 2, pi, 3 pi over 2. Same with sine. The minimum value for cosine is -1. The maximum value for cosine is +1. Cosine of 0 is +1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. Cosine of 2 pi is 1. So what this looks like, and I'm going to illustrate a little bit of that continuation. So we're going to go down to our minimum, and then back up to our maximum, and then it would continue on there. So giving a sketch of what this would look like over multiple periods. Look like something like that. Again, continuing on. And what we've graphed is from here to here. And this, between those two pink lines that I've just drawn, what that is showing is the 2 points where then we start seeing that pattern repeat itself. So that is one period as we've illustrated in this graph. Okay. So now that we have these parent functions for sine and cosine, now let's talk about transformations of these functions. I've given two forms of sine of our sine function. These would also apply for cosine. I just chose sine for the sake of keeping things as simplified as possible. But we really have two forms of these trig functions, these sinusoidal functions, which is another name for periodic functions. One where that factor of b is inside the parentheses or inside the argument. And then the other one where b is still part of the argument, but it's factored out of the parentheses. Now, the main difference between these two forms is how we identify our horizontal shift. So let's start identifying these. First, we'll talk about amplitude. That coefficient out front is going to give us our amplitude. It really translates to what we used to call a vertical stretch or compression, but it's also going to help us define the distance between the midline and the max or the min. So traditionally, we have a amplitude of 1. We're looking at our parent function for sine. Here's our midline. This is the middle of that graph. The different distance between the midline and that max is 1. The distance between the midline and the min is 1. B we call our frequency. It really determines how many periods of our function we're going to have over 2 pi. And the reason it's over 2 pi is because that's the period of our parent function for sine and cosine. So to determine the period for the given function, you're going to take the period of our parent function, 2 pi, and divide it by that value of b. Now, it doesn't really matter whether b is on the inside or the outside of the parentheses to calculate that period. Next, our horizontal shift is represented by c. Now, this is where our two forms become important to be paying attention to. Depending on the form of the function, you would find or determine the phase shift differently. So if we have form 1 where b is inside of the parentheses, then our phase shift is going to be c divided by b. And if we have form 2 where we have factored b out, the phase shift is just going to be c. It's really a toss-up on how you're going to have that function provided for you. So I do think that there's some value in being familiar with both of these forms. If this is too much for you, then cross out one of these forms and cross out how to find the phase shift for that particular form, and just always manipulate the given function to make sure that it matches the form that you are most comfortable with. Another note about phase shifts, this is simply just a horizontal shift. So if you recall from previous classes, like a college algebra class, your horizontal shifts, the direction of the shift is opposite to the sign. So if we have a minus c over b, that minus sign in the parentheses is indicating a shift to the right. If it was plus c in the parentheses, that plus would indicate a shift to the left. And then D is our midline. That's really just showing a vertical shift. So let's look at some examples. Our first example, we want to graph y equals 2 sine of x. Observing the difference between our given function and our parent function. Let me just rewrite those up top. So y equals sine of x, or y equals cosine of x. these are our parent functions, and any value that's added to these parent functions is going to be representing some form of a transformation. Now, where that value lies is going to indicate what type of a transformation it is. So that coefficient out front here, that 2, is telling me that there's an amplitude change. Nothing else has changed. So if I go to sketch this graph, and I'm going to just sketch one period for now. My period is still 2 pi because we haven't modified the period. So let's start by marking off our horizontal axis. Once we've marked our period, again, we divide it into 4 equal parts to be able to plot those 5 landmark points. A start at 1 point at the start, and then 3 in the middle, and then one point at the end of that period. Now the amplitude is 2, there's no midline or vertical shift. So really all that's going to do is change the height of the graph, so that maximum and that minimum of the graph, to being 2 and -2 respectively. Now with sine, when we start at our period, the way we start the graph is at the midline, then it goes up, then it comes back down to the midline, down, back down to the midline. So we started our midline, we're going to go up to the maximum, back to the midline, down to the minimum, back to the midline. And since all of our sine graphs are going to have that shape, we can continue to use that information, that trend, the behavior that we're seeing for every graph. Now, obviously, transformations are going to change. Do we go up? Do we go down? Things like that. But we're going to be working with those same 5 landmark points. Let's graph y equals sine of 2x. So now the difference is that 2, but that's on the inside of the parentheses. Since there's no addition or subtraction of a constant inside the parentheses, we're not going to see any phase shifts here, so that 2 is just going to affect the period. So to find the period of this function, it's going to be 2 pi divided by that value of b, or 2. So now our period is pi. We've got no other changes. So now, just like I did before, I'm going to mark off the end of my period, and now it's at pi, and divide into 4 equal spots, or 4 equal sections. Now, in that last example, because we maintained that same period, those segments in between those 4 equal sections were broken up by pi over 2. Now, since our period is pi, this would be pi over 4, this would be pi over 2, this would be 3 pi over 4, and then pi. There was no amplitude change, so our amplitude is still 1. We're going to start at that midpoint, or that midline, excuse me, go up to the maximum, back to the midline, down to our minimum, back to our midline. And connect those points. Now, one thing to observe, if you were looking at the graph to the left and the graph on the right, they look exactly the same because the shape of sine is not going to change. Really what we need to be paying attention to when we're trying to identify the equation of a function is all of the markings on your x and y axis. Y equals -1/2 cosine x. Again, thinking about our parent function, the only thing that we've really adjusted is that coefficient out front. So the 1/2, I'm going to start with that. That's going to identify our amplitude. So we know our amplitude is 1/2. But what does that negative out front do? That negative out front is going to serve as a vertical reflection. So again, we are thinking back to what we learned about transformations of functions in our college algebra class. That negative multiplied to the function value is going to reflect it vertically, which if you can see in my video, if we reflect vertically, what we're doing is reflecting over the x-axis. Now, we can start by graphing our parent function and make those adjustments. That's oftentimes how we learn how to graph transformations in a college algebra class. But we could also think about what this looks like in terms of sketching out that behavior before graphing it. So if we reflect over the x-axis, what that's going to do is rather than starting at the top and going down, it's going to start at the bottom and go up. So that's what that shape is going to look like. So let's start putting this together on our graph. Again, our period hasn't been changed, so it's still 2 pi. We're going to work on dividing that 2 pi in halves to get our 4 equal sections. Now our amplitude is 1/2. So instead of going up to 1 and down to -1, we're going up to positive 1/2 and down to -1/2. And using that reflection, we're going to start at our minimum, go to the midline, go to the maximum, midline, back down to the minimum. And I am going to draw those little hooks at the end of my periods just to illustrate that it does continue by going back up. Y equals 3 cosine of 1/4 x. So now we've got two, technically the last one did have two transformations because we broke up the negative, that factor of -1 and the 1/2. But in this one, we're going to see two very obviously different transformations. The 3 out front is going to give us our amplitude of 3. And that 1/4 is going to impact our period. Again, that's called our frequency. So our period is going to be 2 pi divided by that coefficient of 1/4. To simplify this complex fraction, we're going to take 2 pi and multiply it by the reciprocal of the denominator, which is going to be 4/1. So that period is 8 pi. The name or the term is called the frequency, that variable is called our frequency. And what I define this as is the number of periods we see in this graph or this function over 2 pi, which means in 2 pi units, we're only going to see 1/4 of a period, which is why we end up with such a large period. But when we scale our axis, we can make our scale look exactly the same as our previous graph. So again, here's 8 pi. We're going to start dividing it in half. So there's 4 pi. Divide that in half. There's 2 pi. Divide this one in half. This is 6 pi. Our amplitude is 3. So that gives us our scale for our vertical axis. Cosine, because we don't have any reflection this time, starts at that maximum, goes to the midline, minimum, midline, maximum. So maximum, midline, minimum, midline, maximum. And we can connect those points. Now, again, what I wanted to illustrate was here's 2 pi, the period of our parent function cosine x. We're only seeing 1/4 of the period of this graph in that 2 pi units, which is what that frequency is telling us. Graph y equals -2 sine of 4 pi x over 1 period. So now we've got a lot going on here. Okay, we've got that negative out front. We've got this 2, and then we have this 4 pi. The negative out front is going to be that vertical reflection, the reflection over the x-axis. So thinking about our parent function for sine, and I'll scroll up to that graph, instead of going up here when we reflect, it's going to be going down from that first point. So just a quick sketch of what that is going to look like. And that just helps me remember when I go to start putting this all together. Our amplitude is going to be 2 from that factor of 2 out front. And then our period is going to be found by taking the period of our parent function and dividing it by 4 pi. So the period is 1/2. Now, just because our period is no longer in terms of pi doesn't mean we're not going to approach this the same way we have before. I'm going to mark off my period along my horizontal axis and then divide by 4. So this is going to be 1/4 dividing it in half. This is going to be 1/8 dividing it by half. So that tells me that this is 1/8, 2/8, 3/8, which can help with those fractions. Our amplitude is 2. And we're going to reflect over that x-axis. So starting from that midline, instead of going up to the maximum, now we're going to go down to the minimum. So midline, minimum, midline, maximum, midline. To create that graph. All right, so now let's look at this graph. And we're going to try to write the equation that's represented by this graph. Now, the directions tell you to write the equation in the form of y equals a cosine bx or y equals a sine bx, where b is greater than 0 for the given graph. Essentially, for any graph of sine or cosine, you can write it in terms of sine or cosine. Now, these directions are maybe not perfect, because if I look at this graph, in order to write the equation for sine, I would need some sort of a phase shift. What we want to observe is, where does one of these periods begin? And when I think about beginning, a lot of times I'm thinking about what's happening at that origin value. So x equals 0. So at x equals 0 on this vertical y-axis, it looks like the graph is at a minimum. Since we're at a minimum, we want to choose cosine. It's going to be a lot more straightforward, and it's not going to require a phase shift. Again, looking at where that graph starts or where a period starts, if it's starting at the midline, we want to use sine. If it's starting at a minimum or a maximum, we want to use cosine to avoid needing phase shifts. Phase shifts are always a little bit more complicated to work with, so if we can avoid it, we try to. Now, since we're actually starting at a minimum, we know that there's that reflection. And we've now seen a couple of examples like this. What that's going to do is just make it so our amplitude, that coefficient up front, is negative. So we've got y equals a times cosine of bx. We know that a is going to be negative, and we can see from the graph the distance between our midline, that midline in this case is going to just be our x-axis, is 4 units. So that means we've got a is 4, but we want to make it negative again because we're starting at a minimum for cosine instead of the maximum. And now we need to find our value of b. If I look at this graph, I can see that we go through one period starting here at that minimum, going up, we get back to another minimum at pi units. So our period is pi. And the way we find our period is 2 pi divided by b. So now we can solve this equation for b. If I multiply both sides by b, we get pi times b is equal to 2 pi, and then divide both sides by pi, we see that b is equal to 2. Now we could also look at this in terms of the graph. B represents the frequency. So how many periods do we see in 2 pi? Since we, again, let me trace this. Here's 1 period. Here's 2 periods in 2 pi units. So that gives us that frequency of 2 as well. So then our equation is y equals -4 cosine of 2x. Now, I mentioned at the beginning of this example that I didn't love the directions that I've written here, and that's because this function, y equals a sine of bx, is actually going to require a phase shift. We're not going to be able to modify or write the equation for this particular graph using sine without a phase shift. For any problem like this, you could always verify that your equation is correct by plugging it into Desmos to graph it. The average temperature in Phoenix, Arizona can be approximated by the function f of x equals 19 sine of pi over 6 x times x minus 4.3 plus 74, where x is the month and x equals 1 corresponds to January, x equals 2 to February, so on and so forth. To observe the graph over a 2-year interval and see the maximum and minimum points, we're going to graph f on the window from 0 to 25 by 0 to 125. Now, this particular function, not something we're going to graph by hand, so we're going to transfer over to Desmos for that. Please make sure you keep your notes handy because I'm not going to go back and forth between the questions. All right, so I've got Desmos open. Again, you can use your graphing calculator. I'm just going to always be modeling with Desmos because it's a free online graphing calculator. If you need any help with your graphing calculator, please don't hesitate to reach out. I'm very familiar with that TI-84, which is the same as the TI-83. All right, so let's enter our function. And I'm just going to use, oh, we can do f of x, that's okay. Equals 19 sine. Now, I do want to illustrate one thing. I used brackets in my example because it helps visually see the difference, the different grouping symbols. But this is going to give us some issues, I believe. I tried it before and it didn't quite work. X minus 4.3, close that bracket, plus 74. And I think, yep, there's that error there. And the error is going to be that we're using brackets instead of parentheses. So we want to replace those with parentheses. Oops. Right there. So all I'm doing is just changing out those grouping symbols. Sorry, ice machine started going. We're just changing out those grouping symbols from brackets to parentheses. Now, if I look, it doesn't look like anything's actually graphed. So now we want to modify the window. Now we gave specifications of that window. We wanted to go from 0 to 25 on that horizontal x-axis, or the horizontal axis, and 0 to 125 on the vertical axis. So we're going to do that in Desmos by going to the graph settings. And I can change my x-axis. We want to go 0 to 25. I'm going to just go by ones. We can change, the step is what units we want to go by. The y-axis, we want to go from 0 to 125. And this we might want to modify, but it looks like it's graphing pretty nicely, so I don't think we need to mess with that. One other thing I wanted to talk about with this graph was just if I go back to the settings, again, anytime we're dealing with trig functions, we need to be mindful of whether or not we're measuring angles in degrees or radians. This is set to radians. Just a quick switch toggle over. If I go to degrees, look how much our graph changes. So we definitely want to be in radians. And one of the key indicators here is that factor of pi over 6. When we're dealing with degrees, we're not going to see factors of pi typically. So that's going to be our cue there. If you have any questions, obviously reach out. The first part of that question was we wanted to observe the maximum and the minimum. So the nice thing about Desmos is that I can kind of toggle around, find my minimum there at 55, and I can just move my cursor around too and see that that is the minimum of 55 degrees. And then up here, there's even already a gray point there for that maximum of 93. And these are in degrees Fahrenheit. The second question asks, according to this model, what is the average temperature during the month of October? The initial problem did indicate that January corresponds to x equals 1. So here's our January. So October would correspond to 10. So I find 10 along that horizontal axis. And then I'm going to start kind of moving my cursor around, trying to get as close to 10 as possible. And I can see that the temperature, the average or the temperature in the month of October is 76.972 degrees Fahrenheit. And then what would the approximation be for the average annual temperature in Phoenix? When we're talking about the average annual temperature, what we're really talking about is the midline. Now, we don't need to use the graph to view the midline. The midline is given by that value added or subtracted from the function in the equation. So it's that plus 74. Returning to our example in our notes, again, that first problem was just asking for the maximum and minimum values. That second part, when they wanted the average temperature in the month of October, we were looking for the function value when x equals 10, which we found to be 76.972 degrees. And then in the last part, what was the average annual temperature? So not the temperature in October, but overall months. And that's going to be represented by our midline, which was 74 degrees.